Tiernan, take it away. And what
Okay. So I'm going to do a presentation. It covers some of the kind of areas that Fiona forwarded me some of the questions, and I kind of thought I'd do a little bit of an overview just on groundwater. And again, I can make the slides available if you want them. There's no problem with that. Some of it is a little bit technical, but I'm not going to do the technical stuff. It's really just to talk a little bit about give you some frame of context for thinking about groundwater, I suppose. This is a guy I work with. This is down in the Burren, and just to show you the water that he's taken a sample of is water that's springing up out of the ground after. This is groundwater making its way to the surface after a rainfall event. And this being Ireland, of course, there's a perfect blue sky behind it. But just to give you a sense of what's going on. Anyway, I'm not going to spend any time on this. This is the definition of what I do, which is hydrogeology. Okay. Now, this will be on the exam. Fiona told me to tell you that. Sorry. The key thing here is hydrology is just the study of water, on the planet. That's it. That's what hydrology is about. And hydrogeology is the groundwater component. And it's the study of water in the ground. But this is the big difference. It's also about the interaction of the ground and the water. That's the really, really big difference, is that once water gets into the ground, this is something just to always be conscious of. The relationship between water and the ground is active. So it's not just simply water going through the ground. It's water going through the ground, but interacting with the ground. The water gets modified by the ground, and the ground gets modified by the water. Okay, that's all you need to remember from this thing. So it's a long, unwieldy definition, but the point is that the water and the ground's relationship isn't just simply a passive thing where water is simply just going through the ground because that's the thing that happens to be in the way. It's interactive. It's completely interactive. So let's talk about some really basic stuff. How much water is on the planet? Okay, before we get to Ireland, if you want. So how much water is on and above the Earth's crust? And it's something like this. It's some ridiculous number. It's a meaningless number, right? It's 1,300. I have to take a pause before I say this. 1,388,3,940 cubic kilometers of water. That's in, on, and above the Earth's crust. So that's a kilometer by a kilometer by a kilometer. Okay, times that big number there, or it's 1.388 by 10 to the 21 liters of water. So there's a lot of water in and on and above the planet. And the key thing to remember is it's tiny. All of the water on the planet makes up 0.1% of the Earth's crust. Even though when we look at the planet from outer space, it's the blue planet. It's literally the water, the bulk of it is the water that's sitting literally on the top of the ground or very close to the top of the ground. And the key thing from our perspective always to remember is essentially the amount of water that's on the planet now is the same amount of water that's always been on the planet, give or take a little bit of change, but certainly for the last 2 billion years, the amount of water in and on the planet is essentially the same. What changes is where the water is. So right now, that's I'll talk about the kind of split of where the water is. So when we roll back to the height of the Ice Age, 26,000 years ago, sea levels were significantly lower because there was more ice, because more of the water was locked up in ice. It's the same amount of water. And if you roll back 500 million years, we were in this thing called the snowball Earth, where essentially there was hardly any liquid water on the Earth at all. It was almost entirely frozen. So it's just the same amount. And everyone knows this thing, the water cycle. It's the basic thing we learn in primary school, and we learn it again in secondary school. But the power of this is sometimes forgotten. The key thing here is that water's constantly moving. Always remember that. It's always the term you see, you can see it on the bottom, it's in flux. Water's in constant flux. It's in the oceans, it evaporates, it falls as snow, as rain. It freezes in the mountains to form snow and ice. It gets down into the rivers and so on. So it's constantly looping and constantly looping. And in places we know, in some, like in the Antarctic ice sheet, some of the water there is hundreds of thousands of years old. It's been locked up for hundreds of thousands of years. Whereas in the atmosphere, the water might only be in the atmosphere for a few minutes. And in oceans, it's about a few years on average. So, and likewise, when we think about this cycle, it becomes really important, because when we're talking about groundwater, it's just water that's part of this cycle. It's not separate from it. It's just an integral part of the water cycle. And when we talk about groundwater, from our perspective as geoscientists, we don't treat surface water differently from groundwater. It's the same water. It's constantly moving between the land surface and the ground. They're not two distinct units that are not connected. So they're always kind of fluxing between the surface and beneath, if you want. So at the moment, the bulk of water on the planet is seawater. 98% of the water essentially on the planet at the moment is seawater. So the remaining 2.5% is what we call the available fresh water, if you have a sense. But off that 2.5%, about 70% of that's locked up in ice. So it's not readily available to us. And the remainder, the bulk of the remaining available fresh water on the planet is in the ground. Because if you look at rivers, lakes, the atmosphere, all living things, the soil and permafrost, that's only 1.2% of the available freshwater. The largest single freshwater resource on the planet is the stuff that's underneath our feet. Okay, the groundwater. And water itself is really interesting. We could spend days talking about water. But one of the key things that's interesting, particularly about water, is that it's a solvent. It's called the universal solvent. Like, this is what we know. And we know this from practical perspective. More substances dissolve in water than in any other liquid, right? More substances will dissolve in water than in anything else. So that's why it's called the universal solvent. So if you make tea and you put sugar in it, the sugar dissolves because it's dissolving in the water. Now, it's hot water, but it's dissolving. If you put sugar in cold water and you stir it, it will dissolve. If you put salt in cold water and stir it, it will dissolve. So sugar, salt, anything you want, if you give it time, if you put oil in water, everyone says the two will separate. Give it time and the oil will slowly dissolve. It'll take years, but it will slowly dissolve into the water. The thing to remember is, if something dissolves in water, it's not gone. It's still in the water. That becomes really important. So, and the water will move it somewhere else. So water dissolves, it transports, and it precipitates minerals. It will dissolve rock. It will move the rock somewhere else, and then it will dump it again. So the water won't keep the stuff all the time. So this is one of these really unfair questions I'm going to ask you. Is there such a thing as pure water? Fiona Stapleton, is there such a thing as pure water?
Well, those ads would tell you if you do the filters, there is, yeah.
Yeah, okay, right. No, there isn't. There is no such thing as pure. The only place you get pure water is in a lab or in the atmosphere. The instant a raindrop falls, that's pure water. And the instant it forms, it's no longer pure because the water will interact with the carbon dioxide in the atmosphere, and the carbon dioxide dissolves in the rain, in the water. So every time it rains on you in Ireland, carbonic acid is falling on top of you. Right? It's an extremely, extremely weak acid, but all rainfall is acid rain. Now, it's not the acid rain that is problematic, but all rain is slightly acidic because the water is interacting with stuff in the atmosphere. And the thing that dissolves most readily in the atmosphere is carbon dioxide, and there's loads of it in the atmosphere. So if you look at this kind of image here, it's just this kind of, it's a good way of thinking about it. We've got fresh water, brackish water, saline water, and briny water. And there's different ways of how we measure the salt content of different waters, or the salinity of different waters. So just to give you some sort of sense of it, the average seawater salinity is 30 ppt, and that's essentially, that's parts per trillion. So a way of making sense of that is, if you got a liter of water and dissolved 35 grams of salt in it, which is a huge amount of salt, right? If you got 35 grams of salt, dumped it into a bottle of water containing a liter of water and shook it up, that would be essentially seawater. That's what you've created there. If you look at a bottle of Volvic, in this case, this is a picture of a bottle of Volvic I took earlier today. This is one picture. Here's a picture I took earlier today. Every bottle of water that you buy will have something like this on the side of it, because it's legally a requirement of every company that sells bottled water that they put this. And you can see it says mineral composition in milligrams per liter. And this isn't the mineral composition of that, what's in that bottle. It's the mineral composition of what they put in their average bottles. So Volvic, you know, the chemistry changes slightly all the time, But on average, this is what any bottle of Volvic will contain. It'll have calcium, sulfates, magnesium, sodium, and so on. And the numbers just essentially relate to the amount of grams of those things in any particular litre of the water. But what's interesting here is you can start in milligrams. And so that's 1,000th of a gram. So you can see even in something like a bottle of water, we've got 12 milligrams of calcium, which is an awful lot less than 34 grams of salt that's in seawater. So when we're interested in this, you can see Volvic water, the dry residue is 130 milligrams per litre. That essentially means that on average, every bottle, 1 litre bottle of Volvic water will have 130 milligrams of salt in it, because all these elements are just salts. So in other words, a standard bottle of Volvic has a salinity of 0.13 grams per litre, whereas seawater has a salinity of 34.7 grams per litre. So seawater, there's enough salt in it that we can taste it. Volvic, there's salt in it, but not enough that we can taste it. Or Galway water, or Ballygowan, or all the other bottled waters that we buy, or the water that comes out of your tap. Every drop of water that comes out of your tap will have salt dissolved in it. And there's no harm. These are naturally occurring elements. Okay. And this is where they come from. This is the key thing. I'm not going to say anything about this other than this gives you some sort of sense of the common elements that we find in the Earth's crust and the oceans. And essentially, it's the same stuff. The salt that we get in the oceans just comes from the ground. It comes from the rocks. It comes from the soil. So it's related to the bedrock. And then when water evaporates from the oceans, nothing can go with it. So the salt gets left behind and it gets more concentrated. And if you've ever been in France or in Spain, where they evaporate seawater to get the sea salt out, all you do is in a very hot climate, you create a little lagoon right beside the sea, just make it really shallow and let the water evaporate. And when it evaporates, all the salt's left behind in your ground and you've got your sea salt. That's how that's all we're doing here. One of the questions was, how do you get water out of the ground then? This is a standard sampling setup that I use. There's a well. This is a domestic well in East County Galway. There's a domestic well. There's a tube that just goes down the well, and this is what's called a peristaltic pump. So the water essentially gets pulled up this tube, which is just a narrow plastic pipe, and it runs into, here, this is a cell that I have a unit in there that measures the salinity, the conductivity, the temperature, and the dissolved oxygen of the water. And then there's a little tap you can see here, and when I'm ready to take the sample, I just fill the bottle in. So there's nothing, you can take groundwater samples any way you want. The standard way we would do it in Ireland is from a domestic well like this, we'll either try and take a sample directly from the ground, because then you're sampling the groundwater. If you take a sample from the tap in the kitchen, you're sampling the groundwater that has come up through the pipes and into the kitchen. So you're not necessarily sampling the groundwater anymore, and particularly if there's a filter in the system. So if you don't have a pump or anything like that, you don't need to borrow or, and these things are very easy to get your hands on, and you can rent them or you can buy them. They're not all that expensive. But one other option is most people, particularly in rural areas who have their own well, they probably have an outside tap. And the outside tap is a good place to take a sample from if you need to take a sample and you don't have a pump, because typically the outside tap is connected directly to the pump. It doesn't come through any filtration system. So if you do need to take a sample of groundwater, say from a farm, and they have a tap stuck to the wall outside the house, take it from there. And the easy thing to do is let the tap run for a few minutes. Because if you take the sample immediately, if you just turn the tap and take the sample immediately, all you're getting is the water that's in the pipe. That's actually just sort of backed up behind the tap if you want. So just turn on the tap, let it run for a few minutes. So it's like, when you turn on the tap and the water's warm, and then after a few seconds, it starts cooling down. Because as soon as you turn on the tap, you're essentially just getting the water that's sitting in the pipe. So in an ideal setting, if you're doing this for a regulatory thing, there are different ways we will take samples to ensure that we're getting a sample from the tap, which is a different thing than taking a sample from the ground. Because the sample from the ground is that's the raw water that's in the ground. Whereas the sample from the tap is probably what people are drinking. And, sometimes there's a difference in the chemistry. And sometimes the problem can be that there's an issue with the piping that connects the pump to the house. rather than the groundwater itself, sometimes. So we can't always presume, say, if you take a sample in a house and if there's an issue, that it's because there's a problem in the ground. It might be something, it might be, but it might also be that there's a problem with the piping or the connection, or it could be that, and this happens quite a lot in Ireland, is that frequently the septic tank might be too close to the pump. So the aquifer, the system itself isn't contaminated, but some of the effluent from the septic might be leaking into the well, and that's what's getting pumped up. So it's not necessarily that there's a groundwater problem. It means there's a connection problem, or that just something needs to be sorted out. Okay. So if we typically, when we take samples, this is what we're looking for. Again, don't worry about the details on this. These are what are called the major anions and cations. So again, if you look at, they've got Na, Ca, Mg, K, SO4, and so on. So sodium, calcium, magnesium, and potassium on the plus side, sulfate, chloride, bicarbonate, and carbonate on the negative side. And these are the things you'll see on the back of the bottles, you know. And the reason we look at these is more than 90% of stuff that's dissolved in groundwater is this, or these things, is, you know, the bulk of what's dissolved in groundwater is sodium, calcium, magnesium, potassium, sulfate, chloride, bicarbonate, and carbonate. More than 90% of dissolved mass, that's what we call this. Anything that's dissolved in the water is going to be made up of some combination of these things. And that's why these things are the ones that appear on the bottles, because they're the things that occur most commonly in groundwater everywhere. And the key thing is they don't make up all the water. The other 10% is all the exotics. And it might be that the other 10% is where the problems might be. So you might have elevated arsenic in the water, but the levels of arsenic might be extremely low, but they might be large enough to cause problems. You might have elevated zinc or lead in the water, or you might have iron in the water. Now, iron's not a health, it doesn't cause any health problems, but elevated iron is really common in groundwater in Ireland. Elevated manganese is really common in groundwater in Ireland. They have no health implications whatsoever. But if you wash white t-shirts, they'll slowly go grey. They'll also start precipitating out in your washing machines, in the dishwashers, in your kettles. They cause real problems with precipitate, stuff that will precipitate out. And again, people report about those is that they'll cause problems with the stuff that they wash, but also they wear out dishwashers and they wear out washing machines much more quickly. Anyway, just as a by the way. So again, there you go. There's the elements again: calcium, sulfate, magnesium, sodium, bicarbonate. That's why these things are on the bottles, because they're the most common things we see in all the water, essentially. But one thing that we do is, if we get a sample, and again, I'm not going to sweat the details in any of this, is if you take a sample of water from the ground or from a stream and you get the chemistry done, you look at those major anions and cations, what you can do is essentially you can fingerprint the water. So, and we plot them on these types of diagrams. And again, don't worry about what these are. This is the key bit in the middle, the kind of diamond shape bit. Can you see my cursor moving there? Sorry, I presume you can you? Can you see the cursor moving? Can you see that?
Yep.
Sorry, I was giving you a thumbs up, but I think you're sharing your screen, so you can't see me.
No, I can't see. Yeah, I can't. Sorry. Yeah. No,
really, yeah, but we can see perfectly. Oh,
no, that's fine.
I look like an angel as well.
Okay. So each one of these little symbols is a separate water sample, and you can see in this particular case, I can't quite remember, but I think there's about 20 samples on this diagram, but these are all from wells in a particular area. This is for a project I worked on a few years ago. And you can see generally the water is pretty much all the same, but you can see there are a few that there are variations. You can see this sample is different than all the other ones, and these two are different, not as different, but the bulk of them are in here. So we were able to identify just from this first pass where the ones that were likely to be problematic were going to be located, whereas the bulk of them were actually pretty much all the same. You know, they were just sort of essentially, no matter what, their chemistry was essentially the same. But if you have all the anions and cations taken, just those major ones, that list we can use. And again, what I can do is, if you do need the information, I can send you a link to a tiny piece of software which is free from the USGS, US Geologic Survey, which you can download. It is tiny. It'll download in about a second onto your machine. And if you have data, you can input it and you can make these images. They're very crude, but they work really well. And it's free. It's completely free software. The only thing is it won't work on Apples. It'll work on every PC, but it doesn't work on Apples. Okay. But I can send Fiona the link for you. So again, don't worry about the details here. That's the kind of water chemistry bit. Now let's talk a little bit about the other side, which is, aquifers, how we define water in the ground. And normally what I would do is here, I tell you what an aquifer isn't before I tell you what an aquifer is. So I'm just going to tell you this. An aquifer is not an underground lake. That's it. If I hear any of you ever saying an aquifer is an underground lake, I'll publicly shame you. With my students, at least I can tell them I'll fail them, but I can't with you. But in Ireland, in law, this is what an aquifer is. It's a subsurface layer or layers of rock or other geological strata of sufficient porosity and permeability to allow a significant flow of groundwater or abstraction of significant quantities of groundwater. That's how they're defined in Ireland. Now, if you go to the north, they're defined differently. If you go to France, they're defined differently. If you go to the United States, every single state will define aquifers differently. Okay? So here's the I'm going to blow your minds. There is no aquifers don't exist. They're like the horizon. Okay, everyone knows what the horizon is. If you stand at the beach and you look at the horizon, you say, "Isn't that a beautiful horizon?" And I say, "Well, what is the horizon? Can you go to the horizon?" You can't, but everyone knows what the horizon is. So likewise, aquifers don't exist in nature. There is groundwater everywhere, absolutely everywhere in the ground. We define aquifers purely on whether we can get sufficient water out of them for our need. Okay, so everywhere you go where aquifers have been defined around the globe, it's about two things. It's about storage and it's about supply. In other words, if you drill a hole in the ground, can you get sufficient water for a sufficient period of time? So is there enough water in the ground? And can you keep taking it out for a sufficient period of time? And that's going to be based on, if you drill a hole in the ground and you can't get enough water for your factory, you'd say, oh, that's a poor aquifer. Whereas you could drill the same hole in the same ground, you get more than enough water for a house, and you say, well, that's a good aquifer because I've got loads of water. So the definition is a human construct. It's about our ability to access water from the ground over a period of time. And now the definitions, when you look at the definitions, they all have something about storage and transmission, about how easy the water can move through the ground and how much water can be stored in the ground. So generally speaking, the more readily the water can move through the ground and the more water that's in the ground, we are likely to say that's going to be a good aquifer. Whereas if we have to work very hard to get the water out of the ground and we don't get that much out of it, we're going to say it's a poor aquifer. But there's water everywhere in the ground. It's the key thing, all right? So that's the legal definition in Irish law from Statutory Instrument number 9 from 2010, the European Community's Groundwater Regs, okay? So in Ireland, everything in Ireland is considered to be an aquifer. Absolutely everything. We have no non-aquifers in Ireland. And this is how we define it. This is how we group aquifers in Ireland. We have gravel aquifers and we have bedrock aquifers. And all of this information is available on the GSI website. And then within that, we have locally important or regionally important. And in bedrock, we have regionally important karst systems, we have locally important systems, and we have poor systems. And poor systems, the poor aquifer, PL or PU, that's as close as we get to Ireland to saying this is not a good aquifer. Whereas the RK ones are the ones we are saying, this is a really good aquifer. If you have an industrial need, if you're trying to provide sufficient water for a town or a village, if you get the water out of one of these, you're going to meet that need. But you may not, in the ones at the bottom, you might get sufficient water for a single house, but you mightn't get enough water for a town or a village. Okay. And then when we look at it on the map, the image on the left is the bedrock geology, and the image on the right is the aquifer map of Ireland. And again, you can see Northern Ireland has no aquifers, largely because they're defined differently. There's a different use, there's a different definition. So with the geology, our geology crosses the border because there's agreed ways in how we describe rocks. But there's a different law in the UK and Northern Ireland about how we define groundwater in the subsurface. So the definition is different. So you can see the colours in Ireland all line up with the geology. So aquifers in Ireland are defined strictly by the bedrock that we find under them, because that's the easiest way to do it. So if you look at up in Donegal, poor old Donegal's got pretty much the entire, all of Donegal is essentially classed as a poor aquifer. Some of it down around Bundoran, or sorry, around Donegal town itself is better, higher classification. Whereas if you come down towards the Burren, say for example, this swathe from running down through Mayo, East Galway, and into the Burren and into Clare and North Limerick, this kind of turquoisey color that you can see here, these are the regionally important karst systems. And they line up with the regionally important, this is where we see the karstified limestone. Whereas you can see the stuff, the bedrock we see in Donegal, that bright yellow and bright red stuff, that's really tough, resistant bedrock. Water tends to stay on it rather than get into it. It's easier for water to run off it than it is for water to get into it. Whereas down here in the Burren, it's actually easier for the water to get into the ground than it is for it to stay on the ground. But if you look over at the cliffs at Moher, you can see the classification changes because the bedrock changes. So in Ireland, what we do is literally the aquifers are defined entirely by what's underneath them, the bedrock underneath them. And these are what are called regional classifications. So even though up in Donegal, everything's kind of classified as a poor aquifer, you could actually drill a hole in the ground and get a huge volume of water out of a borehole in Donegal. And we've done this, I've seen this down near Kinvara, where adjacent houses have drilled into the ground, and we have had one house, they're saying, we have more water than we can deal with. And their neighbor has drilled 3 or 4 boreholes and hit no water, even though it's classed as a regionally important karst system. It doesn't mean it will guarantee you loads of water. It just simply means you're more likely to get lots of water. Where you get these zones where water can be carried, you're going to get loads of water. Whereas in Donegal, the regional classification is that they're not great aquifers, but that doesn't mean at any particular location, you may not hit a good source of water. And that's likely maybe because the rock is broken or has been modified somehow. Okay. This is the maths part of the evening. And I'm only just introducing this purely to introduce one term, right? This is what's called Darcy's law. This is the governing equation of groundwater flow. I'm not going to say any more than that about it, other than this is what we use. The Q on the left-hand side of that essentially refers to the amount of water moving through time. This is how we use this equation to work out how much water moves in the ground. And the key thing for your guys' perspective is this K value that sits in the middle of this equation. This is called hydraulic conductivity. It's measured in velocity. It's essentially the speed that the water travels through the ground. Okay, so the K is what's called hydraulic conductivity. And the definition of it is, it measures the ease with which a fluid passes through a medium. In other words, it measures the ease with which water will pass through the ground. It is synonymous with permeability. So technically, people will talk about permeability or hydraulic conductivity, and they mean the same thing. So when we talk about how permeable something is, we're essentially meaning how quickly or not water can move through it, which is completely different from porosity. We won't talk about that. And so these numbers, these ridiculous numbers on the right-hand side of your screen are generalized values of what we see for geological materials for hydraulic conductivity values. So you can see gravel has hydraulic conductivity values 10 to the minus 4 to 10 to the minus 2, whereas shale has values 10 to the minus 13 to 10 to the minus 9. These numbers are entirely meaningless. I struggle with these things. So one of the things I always do is I try and convert them into something that makes a bit more sense to me. So if I look at gravel, all these values up here, I've just converted them into, moved them from meters per second to meters per day. And essentially what this tells us is, if I have water moving through gravel, on average, it'll move at somewhere between 26 to 260 meters per day. Okay, that's the speed on average water will move through gravel. 26 to 260 meters per day. That's the top of the conductivity range for water in the ground. If you go down to the bottom, unfractured igneous and metamorphic rock, hello Donegal, in other words, right? These values are 10 to the minus 14 to 10 to the minus 10. you can't convert this into anything meaningful. Look, that still comes up at, on average, the water is going to go at a speed of 0.0009 millimeters per year, or up to a racy 0.6 of a millimeter per year. That's how quickly water will move through the ground. Now, from our perspective, that's essentially impermeable. That's where impermeable comes from. From our perspective, that essentially is impermeable, because even over the course of a human life, even over 100 years, it's still not, you know, at the low end of the scale there, it's still not even going to have traveled a millimeter. But geologically, we've 4.6 million years of time to play with. So everything, water gets through everything, okay? And then just one more on this is a value of clay, because this is an important one to think about. Clay has a very low conductivity, hydraulic conductivity as well. And you can see here, typically water will get through clay at a rate of about 0.3 mils per year, up to about 15 centimeters a year. And if you've ever tried to drive across a clay field that has water in it, clay fields or soil that has a lot of clay in won't drain. And the reason it won't drain is because it's so difficult for the water to get through it. Right? And there's your answer. And this is why when we make landfills, we line landfills with clay. We line it with clay. And it's not because clay is easy and cheap or anything like that. It's because if you pack it down, it takes ages for water to get through it. And that means if you leach it in a landfill, then it's going to take at least, if your layer of clay is only 30 centimeters thick, you can see even when it's going really quickly, the water will still take 2 years to get through a layer of clay at the bottom of a landfill, by which point it's probably denatured. Anything that's in it is probably gone. There's probably no harm in it at that point. And we use these K values to work out source protection zones. This is what we use to build source protection zones. Because what we do is we use what's called the 100-day time of travel. You might have heard of that term. And this is essentially, one way of thinking about this is, if you put a drop of water into the ground, how far will it travel in 100 days? And if you know what the ground is made of, you can use the hydraulic conductivity values to say, okay, given that it's a clay and the conductivity of clay is 0.3 mils per year, and you just divide that down by 365 to find out how far it'll travel in a day, and multiply it by 100, and that'll tell you how far it'll travel in 100 days. And you draw that line on the map, which is called the 100-day time of travel. And that's how you determine a source protection zone. And the reason they picked 100 days is generally most bacteria that we find at the surface will not survive in groundwater for more than 50 days. So when they were defining this, they said, just to be sure, instead of using the 50-day time of travel, we will use the 100-day time of travel. So if you put a drop of water on the ground and it gets into the ground, you should be able to work out how far it will travel in 100 days. And say another way of thinking, if you've got an activity going on, if you're, say, got a fuel depot, or if you've got a slatted shed, or if you've got a water treatment plant where there's discharge, but you've got a well in proximity to it. If you know that the direction of groundwater flow, if it's flowing from the source of possible problems towards the well, we can work out the 100-day time of travel and say, well, actually, by the time any drop of water that has arisen from that first location gets to the well, it's 200 days. So any bacteria that's in there will be long dead. So there's not going to be any problem with that. That's how we work out source protection zones. Okay, it's as simple as that. And then all you're doing is you're mapping them using GIS mapping techniques. And we need to know which way the groundwater's flowing. That's easy to do. Once you know the direction of groundwater, you just work out backwards from your point, based on the hydraulic conductivity of the system, how far any single drop of water, and therefore any single drop of contaminant, could travel in 100 days. And then you just start marking that on your map, join up the lines, and you've got your source protection zone. So chemistry reflects the bedrock, which is the lithology, because the water will interact with the bedrock. It reflects soils, because the soils sit on top of the bedrock and the water interacts with them. It reflects time. The longer water's in the ground, the more it will dissolve. It'll reflect the flow path, how water gets through the ground, and it'll affect the exchange rate, which is the chemical interaction between the water and the ground itself. So water contains elements, which are minerals, which are salts. So when you talk about salt water, when we talk about mineral water, when we talk about elements, they're all the same things. And here's the philosophy, if you want, just to finish up. All of these elements, minerals, and salts, they're all found in the crust. So water, essentially, groundwater in particular, is just liquid rock. And to finish with a flourish, the sea is around us, but the river is in us. In other words, we're liquid rock as well, because we're made of the elements that come from the ground. And the bulk of us is just simply water as well. That's me. I'm done.
That was brilliant. So obviously I did the Earth and Ocean Science degree, so I have heard a lot from Tiernan before, but even then I was learning a lot again. Like I think what was so good, that what I really enjoyed there, Tiernan, was I learned about K values, permeability, conductivity, did all the equations, but I didn't do what you did there, which was look at it in meters per day. And now I can visualize that. I can say,
exactly.
oh, I can look at that system.
Yeah.
And when you describe the landfill and leachate and thinking, okay, if there's a 30 centimeter layer of clay, that will take 2 years. This makes it all so much more practical than just spouting out values all the time, which I think engineers are really guilty of doing. Engineers can kind of say, oh, this is that, or this is whatever. Their geotechnical sort of way of speaking, it does not help the public or even other experts who are just not engineers or geotechnical experts to really work together and create systems like for the community or for developments that we need to speak in these ways that where everyone can be just understanding it. And you've made it so, I find anyways, very, very understandable. I'll throw it over to you, Liz, because I mean, I did a master or a degree in it, but from your perspective, how did that go from the River Trust members' perspective?
I thought it was excellent because I was in a meeting today for the Deal is one of the rivers in Limerick. And even the map you showed, Joe, Limerick has got, it looks like it's got good groundwater accessibility. And I'm just going to share with you, do you know the ESM tool that UCD have?
Yeah.
Can you see that?
Not yet, but yes, now I can. Yeah, gotcha.
Okay.
Yeah.
So I just turned on the water and the water abstraction points. And I showed this to people today and they were saying, why has Limerick got so many abstraction points? And like South in Cork, it's poor. Like, well, why has Limerick got so many and the other places have so few? So I sort of understand now in terms of what you're saying, it's the rock type. All these things are influencing, but
well, just while you're there, if you can you zoom in on that, or will allow you to and exactly where you are, right? So if you just like hover over, if you go left of Limerick, you'll see Newcastle West. If you keep going left, kind of just there-ish, in about there is Newcastle West. That's where Ballygown is based. Okay.
Yeah.
So Ballygown takes water out of the ground. And Ballygown has been taking water out of the ground commercially for the last, 20 or 30 years. And the ad, they've started running it again. I think it says it's something like 800 years of purity bottled, isn't it? Something like that they use. Yeah, the Ballygown water is about 2 weeks old. That's it. It's only been in the ground a couple of weeks.
Okay.
If it was 800 years old, it would be undrinkable because it would have so much salt dissolved in it, you couldn't drink it. Plus, if it was 800 years old, it would suggest that there's a big, deep reservoir of water in the subsurface. And if there's a big, deep reservoir and you've been pumping out commercial volumes of this over the last number of years, you'd have drained it. So the reason there are so many abstraction points there is firstly because the bedrock is porous and permeable enough that, generally speaking, you're going to hit water wherever you drill. But there's also faults and fractures in the rock, and that's what Ballygown have tapped into. It's not, obviously saying the water's 800 years old of purity bottled, it sounds much better than 2 weeks old, And I mean, essentially, they're just taking water out, and all they're doing is screening it, because all they're legally allowed to do is just take out any material that's in it. They can't treat the water in any way. But one of the reasons there's so much abstraction there is it's on the west coast. It's wet, so there's loads of water falling out of the sky, replenishing the groundwater.
But so actually, interesting. I'm just going to show you another. I don't think that's going to show up. I've stopped the share. One sec.
Oh yeah.
This work for me.
This is the water capacity one, is it?
Yeah. Can you see that?
Yeah. Yeah.
Okay. So this is my problem from Rivers Trust point of view. So water capacity, and this is from the County Council. West Limerick has no more capacity for any more connections to the current water supply. That's what the County Council is saying, and this is a major problem for development in the county. And then I also had telling me that currently they're abstracting from groundwater for the processing, and they now want to start abstracting from the River Deal.
Yeah.
And what I'm wondering is, first of all, I don't think there's capacity to abstract from the Deal. The Deal is already, like most of County Limerick, is really heavily arterially drained.
Yeah.
And even in the most recent EPA consultation document, nearly all our rivers are now going to be designated heavily modified water bodies, which they are, unfortunately. But the Deal is just so heavily sedimented. So it's the rivers in Limerick, we're flat and slow moving, like they're completely different to Donegal, for example. But the amount of water that's been abstracted in the other map, the ESM map, and you see this map and you're going like, and you were saying, that there's water all underneath, but is there a point where there is a problem with over abstraction?
Yeah, of course there is, because that, and I think this is where sometimes people think, oh, there's this unlimited supply of groundwater, and it is the largest resource we have, but it's just rainwater. That's all it is. Do you know, like when we're talking about where the groundwater comes from, it's the stuff that falls out of the sky every single year, and it's not water that's spending a long time in the ground. So if we have a dry summer, people's wells start drying up, and if you've got a shallow well, you'll have problems in the summers. A lot of people will say that, like in East Galway, a lot of people say, they'll go onto the public scheme during the summer because they can't get a stable supply during the summers. And then during the winter, when there's loads of water around, they'll just go back to their own wells. So yeah, there is a point at which you're essentially mining the resource, which is the water resource. And I wouldn't even separate it into a groundwater or surface water resource, because it's the same thing. The water that's in the river is interacting with the ground anyway. So it's not like you're saying you've just got water on the surface and we've got this other resource underneath it that's magically replenished from somewhere else. It's being replenished from the same system. And if we take too much water out of that, it's just like if we took it out of a reservoir. If we said, well, we've got a reservoir that's 100 meters by 100 meters by 10 meters deep, but if we're taking out more water than the reservoir can hold, and essentially that's what's happening in systems like that. And there's a combination of things, probably something like, say, Ballygown. I'm not blaming them, because they're just commercially producing and they have a license to do it. So that stuff has been taken out of the system. So they're pumping it out and it's going somewhere else. So when it goes back into the ground or into rivers, the bulk of it's not going back into the ground where it's being tapped. It's going into the ground all around Ireland, or it's going into the ground wherever Ballygown sell their water. Whereas APB, when they're finished processing that water, it's being discharged probably relatively locally, but it might be going into the Shannon, You know, once it's been treated, it's gone into the Shannon. So essentially, it's been dumped out of the system. They're taking it out of the ground or taking it out of the river, but they're not returning it to that system. And in an ideal setting, what you'd want is you'd want to say to APB, take as much as you want, but you need to treat it to the standard it was when you took it out of the ground. And when you're done with it, you put it back into the system where you took it out. Now, they won't like that because it's expensive to do that, you know?
Well, in that area, so you have APB, which is in Rathkeil. Then when you get down towards Eskeaton, you've got Wyatt's, which is Nestle. And then after that, you've got Ahanish.
Yeah.
And that's not then including all the people who live in that area.
Exactly. All just the domestic wells, you know? Yeah.
And even the public supply.
Yeah.
For there, like it's huge, but it's just getting to grips with the amount of abstraction. So I understand why the council has put up, this map and showing that West Limerick doesn't have any more capacity for connections to the current water supply system that's there.
Yeah.
No, listen, Tiernan, I have learned so much from you in the past 40 minutes that it just everything sort of coming together. And I suppose that's what we do as Rivers Trust, and that's what the iCatch network was formed to do, was where we share information and also we learn from each other. And Fiona, thanks you so much for getting Tiernan here today.
Listen, I find that inspiring, Shirley, and I love the way you use the language that it was easy for us all to understand. Well done. But I'm just wondering about the whole denaturing process. Obviously, water has been on the go and the cycle goes on and on. But I'm just wondering, obviously, with all the nutrients, whether it be phosphates or nitrates or chemicals such as what we use on such a large scale since the whole agricultural era started. And you're talking about the denaturing process. Can you kind of explain that a wee bit? I can't understand how this stuff can disappear or whatever, or do you have an understanding of that, or could you maybe?
Yeah, well, it's not, it dissolves. So some materials dissolve readily in groundwater and others don't. So phosphorus, you tend not to get a lot of phosphorus in groundwater.
Okay.
Simply because it gets stuck in the soil. Phosphorus tends to stick to soil. It likes sticking to soil.
Right.
So, if you think water washing through the soil, any phosphorus that's in there, it prefers to be stuck to the soil rather than in the water. So the phosphorus gets pulled out of the water by the soil itself, whereas nitrates don't. Nitrates wash through. So what we generally see is in the ground, we typically have nitrate problems, but not phosphate problems. In surface waters, in rivers, we tend to have phosphate problems because if a farmer spreads stuff on the field and then you get a big rainfall event, an awful lot of it just runs straight off into the nearest ditch or the nearest drain or the nearest stream. There's nothing, because I think one way of thinking about this, and you have to be kind of careful about, not giving water animation or something. Water is lazy. That's a good starting point. Water will take the easiest route possible. And there's a physics basis for that. If you want to look at it from that perspective, it's about energy conservation. So essentially, water is trying to conserve energy as it moves. So it'll simply take the easiest route possible. If it's easiest for water to go down a hill, that's what it'll do. If it's easier for it to get into the soil, that's what it'll do. So somewhere like, East Limerick or West Limerick is very flat. So any water that's moving, any rainwater is going to stay on the ground longer. So it's going to move because there's nothing to drive it. Whereas up in Donegal, out in Connemara, when it rains, you've got those steep slopes. The water's going to come shooting down the hill because it's the easiest thing for the water to do. So the longer the water's in contact with the ground, the more likely it will interact with anything that's in the ground or that's been added to the ground. So that's, where you have the natural occurring minerals or elements, all of those things are the stuff that the soil is made of or the bedrock's made of. Where we tend to get problems with chemicals, a lot of chemicals, some of them dissolve in water. So these will be man-made chemicals and they'll get transported and then they become problematic. Whereas some of them don't, like oil, generally speaking, from our perspective, over the course of a few weeks, say if you have an oil spill, the oil will stay on the water rather than going into the water. And generally speaking, it's relatively easy to fix an oil spill in a river or even in the ground, because the oil will float on top of the water if you get it quick enough. If you leave it for a few years, it becomes way more complicated because it actually starts interacting. The two of them will start interacting.
Okay, very good.
And I mean, I like some of the other issues that we're seeing now, like you get these things, what they're calling about, or I can't remember the term they use. It's not novel. There's emerging contaminants now that we're really concerned about. So we're starting to see now in groundwater, not just in Ireland, this is globally, we're starting to see pharmaceuticals starting to show up. Now, this isn't from pharmaceutical companies. This is from people flushing stuff down their toilets. You know, they're peeing in their toilets and they're flushing. And a lot of the drugs that they're taking for whatever that they're getting, a lot of those things flush straight through your body. So they go into the toilets, they go into the treatment systems, but they're not treated because they're not extracted, because that's not what the treatment system set up. And if the more and more drugs that we take, you know, prescription drugs or whatever drugs that we take, what we're seeing is that they're now starting to show up in groundwater, and they're starting to show up in rivers as well. Now, they're not at concerning levels, you know, they're not at issues that that you could drink a glass of water and worry about what it's going to do to you. But they are now these are things that we're probably going to have to start looking at or start legislating. And at the moment, there's no real legislation. And there's no way of stopping it, because it's not from a single point. It's from the entire island. You know, it's not like you can say, there's the pipe, and you've all heard that term, a point source, haven't you?
The
way I learned this was, it's the thing you can point at. And I still work on that. If you can point at it and say, look, it's coming from there, that's a point source. Whereas if you just wave your arm around and say it's coming from this entire valley, that's a diffuse source. You know, there's no one single point that the problem can be sourced. So going back to West Limerick, you can see there's abstractions across the entire area. And because there's so little, there is water getting into the system, but it can't meet the need. So you can't just, you can't turn off the water supply to, tens of thousands of people. You can't say, well, it's your problem. You need to stop taking out your 200 litres a day or 300 litres a day or whatever,
In terms of one of the questions that I've asked Fiona is the amount of water that's been abstracted collated anywhere?
Oh, okay. In certain places, certain counties do. So Roscommon will, and I think Laois as well. And that's simply because certainly Roscommon gets about 90% of its drinking water supply from groundwater. So Roscommon County Council would have a good handle on what that number is. Whereas groundwater provides a significantly smaller proportion of most drinking water supplies to other counties. But the problem is it typically gets really skewed by large cities. So look, County Galway, for example, if you take County Galway, the bulk of drinking water in County Galway is from Lough Corrib, because the largest single user of water from Lough Corrib is Galway City. The biggest population centre in Galway abstracts water from a lake. But East Galway, the bulk of the water, the bulk of water supply for group schemes is from the ground. So there's the council, Irish Water probably have a decent handle on what the group schemes are taking out and what the bigger schemes are taking out, because they're in charge of the group schemes now. And the group schemes would be very good at they know exactly how much they're taking out of the ground every year, because there's a cost to it, because they know it, they need power to pump it up. So they know exactly how much they're taking out. So Irish Water would be a good source, except Irish Water aren't very easy to contact. So, I mean, an ideal way would be go through the county council. If you know someone in the council in water services, that would be a good starting point. Irish Water are kind of loath to talk to the public. I kind of understand why, so, they'll have a kind of info at Irish Water. That's what you kind of have to send their stuff to. But if you know someone in the local authority,
will they also have the data, the water abstraction that's done by companies? So like, I mean,
yeah, because anything under license, anything that's been taken out because they've an abstraction license, you get all of that information be available. And I would say Irish Water would have county by county abstraction totals.
I don't know whether the Irish Water necessarily would have the handle on the abstraction rates of group water schemes. I think that's still controlled by the local authorities, from what I understand.
Yeah, it is, but they're Irish Water are now in charge of all water in Ireland. So local authorities have to report that to Irish Water.
Oh, okay.
So they're legally required to report it to Irish Water.
That information is always available on local authority websites as well.
Yeah, and that's the problem. The information's out there. You might have to go to loads of different sources to get it. Whereas actually, if you could get into Irish Water, they could probably just give you the number right away, you know?
Yeah.
Okay.
Sorry.
Oh, you're still talking, Tiernan? I'm just going to call in to tell you that it's 9 o'clock. So I'm the sort of person that appreciates being told when I start and when I finish. So I'm just saying to you, Tiernan, thank you so much.
No problem.
If there's anything else you want to say, I caught you mid-sentence there. No, you're good. Great. Okay.
Thanks a million, Tiernan.
So that was brilliant. I got so much from that, and I just really enjoyed it. So I'm absolutely delighted that this is what this workshop was. And Tiernan, there has been a few excuses, or apologies, and they all want the recording of this. And I should have mentioned to you, is it okay if we share that, because they're really good at, if they miss a workshop, they actually watch the recording.
No problem.
I'm sure we'll be definitely recommending for them to do that. Okay, thank you. So everybody, this is it. It's 9 o'clock. So I'm going to say thank you so much to you all.
Thank you. Thanks, Fiona. Thank you,
Thanks,
Tiernan.
Andrew.
Really appreciate your time.
No problem. And if you need any information that I can, just get on touch with Fiona. Fiona can ask me, and I can send stuff to Fiona, or I can send you links to other things. So,
One thing I would say, Tiernan, please send me the link to that bit of software that makes those impressive looking triangle diagrams.
The FSU one. Yeah.
No, so I got the FSU link, which was the flood map for the engineers. We're on that. It's the other one that you said, when you get the samples of water and you put them through this software.
Yes, of course. Sorry, absolutely.
Show you where the fingerprint is different.
Yeah, no problem, Fiona. Yeah, sorry. Yeah, gotcha.
Lovely, thank you, brilliant. Yeah, so that's the only thing. Everyone else, I actually screenshotted as Tiernan was talking, so I've got his slides more or less in the workshop slides that I'll be emailing you. So it's documented anyhow. So there we go. I will be in touch with you all before next week, and it's hoping that there's project drafts for us to discuss by next week, because it is our final workshop. So thank you so much. And get in contact with me if you have any problems.
Could I ask one wee question?
Go for it, Sally.
Okay. In QGIS, I've lost the little site on the left to get out of it.
No problem. Tiernan, I can let you go. I'm going to share my screen here. Sally, I know what you're talking about, because it does always happen, and it happened to me a few times. And I'm going to share the screen. Anyone else that wants to leave, feel free to go. Otherwise, you can watch me go through this. Thank you.
Okay.
All right.
Thanks,
see you, Fiona.
Thank you, everyone.
Bye-bye. Thank you.